Now, it's important to realize that a transformer doesn't add any energy to a circuit. It merely changes or transforms the energy that already exists in the circuit from one voltage level to another. The total amount of energy in the circuit must remain the same. Now, if it were possible to construct a perfect transformer, there would be no loss in power in the transformer. Power would be transferred from one voltage current level to another. Since power is the product of current times voltage, an increase in voltage by means of the transformer must result in a decrease in current. And likewise, a decrease in voltage by the transformer must result in an increase in current. Now, stating it another way, we can say that a transformer which increases the voltage by a given ratio will decrease the current by the same ratio, and vice versa. For example, if we apply 10 volts at 10 amperes, or a power of 100 watts, to the primary of a step-up transformer, which has a turns ratio of 1 to 10, the voltage in the secondary would be 10 times that of the primary, 100 volts. But the current in the secondary would be 1/10 that of the primary, 1 ampere. The power in the secondary, however, would still be 100 watts. Now, let's suppose the same 10 volts at 10 amperes was applied to the primary of a step-down transformer, one which has a turns ratio of 10 to 1. The power in the primary would again be 100 watts. The voltage induced in the secondary would now be 1/10 that in the primary, 1 volt. The current in the secondary would now be 10 times that in the primary, 100 amperes. The power in the secondary, however, remains at 100 watts. Now, thus far, you've seen that if the secondary of a transformer has more turns than the primary, the voltage is stepped up. Whereas if the secondary has fewer turns, the voltage is stepped down. Now, later you'll see transformers in which the primary and secondary have the same number of turns. Such a transformer has a turns ratio of 1 to 1. Unlike the step-up and step-down transformer, a 1-to-1 transformer neither increases nor decreases voltage. The voltage and current available at its secondary is the same value as that applied to its primary. Now, the transformers we've dealt with thus far were assumed to be ideal transformers. That is, they were considered to be 100% efficient. Such an assumption is quite all right from a theoretical viewpoint. However, from a practical viewpoint, the construction of an ideal transformer is an impossibility. The primary reason for this can be realized by discussing a factor known as the coefficient of coupling. The coefficient of coupling, which is represented by the letter K, is a measure of the degree of coupling between the primary and secondary coils of a transformer. The coefficient is obtained by dividing the number of magnetic lines cutting the secondary coil by the number of magnetic lines actually produced by the primary coil. For example, if the primary of this transformer produced 10,000 magnetic lines, but only 8,000 lines cut the secondary, then the coefficient of coupling would be equal to 0.8. Now, if all of the magnetic lines produced by the primary coil of a transformer were to cut the secondary coil, the coefficient of coupling then would be 1. The coefficient of coupling for an ideal transformer is also 1. However, even with high permeability iron cores, a few of the magnetic lines fail to cut the secondary and are, in effect, lost. Now, this prevents the coefficient of coupling from ever being exactly unity, or 1, in an ideal, or I should say in a practical transformer. It should be pointed out, however, that a coefficient of coupling of 0.98 is possible between the coils of a well-designed transformer. Now, in general, there are 4 types of transformers. They include power transformers, audio transformers, RF, radio frequency transformers, and finally, auto transformers. Power transformers are used to step up or step down AC voltages occurring at the power frequencies, which you'll recall include 50, 60, and 400 cycles per second. It should be pointed out, however, that a particular power transformer is designed to operate at only one of these frequencies. For example, a power transformer that's designed to operate at 60 cycles per second couldn't be operated at 50 and 400 cycles per second. Now, quite frequently, and especially when dealing with schematics, you'll have to recognize a type of transformer by its schematic symbol. The schematic symbol for the power transformer can usually be identified by there being more than one secondary winding. In this case, there are two secondaries. However, other power transformers may have a different number. You'll notice that each secondary has a different number of turns. One of the secondaries has fewer turns than the primary. Therefore, it produces less voltage than that applied to the primary. The other secondary, though, has more turns and thus produces more voltage. Now, you'll also notice that the power transformer is constructed with an iron core. Now, unlike a power transformer, which is designed to operate at a specific frequency, the audio transformer is designed to operate over the entire range of audio frequencies, which is generally considered to be from 20 to 20,000 cycles per second. The schematic symbol for the audio transformer resembles that of the power transformer. The audio transformer, however, usually has only one secondary winding. Like the power transformer, the audio transformer, too, is usually constructed with an iron core. Well, at frequencies above 20,000 cycles per second, the RF transformer comes into use. At these frequencies, hysteresis and eddy current losses in an iron core become so great they have to be prevented. Therefore, RF transformers generally have an air core. The schematic symbol for an RF transformer, then, is easily identified by there being no vertical lines between the primary and the secondary coils. Now, a special type of transformer which uses only one winding for both the primary and the secondary coils is the auto transformer. In addition, an auto transformer can be used either as a step-up or as a step-down transformer. When used as a step-up transformer, all of the primary winding is part of the secondary winding. Here you see that the winding has a total of 1,000 turns. 600 of these turns serve as the primary, while the entire 1,000 turns serve as the secondary. Now, when an auto transformer is used as a step-down transformer, all of the secondary winding is part of the primary winding. Here we see now that the entire 1,000 turns are serving as the primary, while only 600 are serving as the secondary. Now, auto transformers are sometimes constructed with a sliding contact, as we see here. When a control is varied on the transformer case, the secondary voltage can be varied from the maximum voltage induced in the winding down to 0 volts. As you can see, this type of transformer is called a variable auto transformer. However, it's probably most commonly known as a variac. Now, auto transformers are normally used in power circuits. However, they may be used for audio or RF use. That is, designed for audio or RF use. The symbol for an auto transformer used in a power or an audio circuit will indicate an iron core. The symbol for an auto transformer used in an RF circuit will be the same, except it will not indicate an iron core.